So remember last lecture, we talked about stuff like strings and functions, right? And in a string, you have a bunch of, an alphabet of letters, and a string is just a way of writing those letters one after the other, but there was no restriction on how you write the letters, right? It was just write them down, and you can repeat letters or whatever. Now what I want to understand is, what about a string? How many strings are there where you don't allow repetitions? So, recall that there's 26 letters in the English language. Here's a kind of example question. So how many strings of length 5 are there using the English alphabet such that each of the letters are different? Or all of the letters, I just mean you don't have any repeated letters. Anyone got any ideas? Well, it all comes down to this rule of product again, right? So how many choices are there for the first letter? So for the first letter, you've got 26 choices, right? There's no restriction. Now think about it. Once I've chosen the first letter, suppose it's D or something. Yeah, the only restriction now is that you've lost the choice of D, right? So you now have 25 for the next one, 24 for the next one, 23, 22. And by the rule of product, the answer is going to be what you get by multiplying all these numbers, right? Okay. So that's this is just a basic example which illustrates what's going to, so now we're going to kind of talk about this a bit more formally. So let X be a set. So you can think of it as an alphabet. So if I take a string of letters in X, we call it a permutation if all of the letters SI are different. In other words, what I mean is that there's no repetitions. One thing to notice is that if I have a permutation of X, which has length n, well, you can only do that if n is less than the size of X, or sorry, at most the size of X. Right? Because I can't take three things. In some sense, you can't take three different things and write a list of 4 of those things in order or something, because there's only 3 of them. This is just to say that this definition only makes sense when n is at most the size of X. So for n at least 1, define n factorial to be, so the notation is you write n with an exclamation mark, and what this means is n times n minus 1 times n minus 2 all the way down to times 2 times 1. Right? You just multiply all the numbers, or if you want to write it the other way, it's 1 times 2 times 3 times 4, blah, 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 all the way up to n. This definition only really makes sense when n is at least 1, because how can I multiply all the numbers between, if you take 0 is kind of a weird case, basically. But by convention, we define 0 factorial to be 1. So please do remember this. 0 factorial is not 0. 0 factorial is 1. Okay, so another definition, we define Pmn. So suppose m is at least n, which is at least 0. We define Pmn to be m factorial over n minus m factorial. So we have a question. So when the domain of S is the numbers 1 to n, there are n slots. But when we take from the alphabet, we have n minus 1 slots, and then size of x minus 1 items left. Yeah, so this is essentially, this is what a permutation is. Yeah, you list the elements. Basically, a permutation of x, you list some of the elements of x in order. But you don't have to list all of them necessarily. So permutations of the same set can have different lengths. So what is the purpose of this Pmn? Actually, maybe I'll kind of, so what is this first of all, right? So on the numerator, you have m factorial, which is, you multiply all the numbers from m down to 1. On the bottom, you have, ooh, I've messed that up actually. sorry, this should be m minus n factorial. But that's just equal to m times m minus 1 times m minus 2 all the way down to m minus n plus 1. Okay, this is just by the definition of factorial and by canceling. This is the type of number that we were getting before. Remember when we were taking words where every letter is different, right? We had 26 times 25 times 24 all the way down to I think 22 or something in that case. This is the same sort of thing. So if m is, we have m times m minus 1, m minus 2, down to m minus n plus 1. So what I claim is that, so suppose we take a set X with m elements, the number of permutations of X of length n, I claim is equal to Pmn. So can anyone think of how you would prove this? Or what kind of rule or what kind of, yes, 0 factorial is 1. Induction, that's interesting. Yeah, you could definitely prove this by induction if you wanted. I'm going to just go directly without any induction because I think that that's going to, to be more convenient. So what I'll do is I'll just use the rule of product, right? So how many choices for the first element of the permutation? So I'm making a permutation of length n. How many choices for the first element of the permutation? And yeah, I would say it's m because any element of X is okay at that point. So you have m choices for the first. Once you've chosen the first, the only restriction for the second is that it can't be equal to the first. So basically, every element of X, except for the one you've already chosen, can be chosen next. So there's m minus 1 choices, right? And then for the third, there's m minus 2 choices, because it just can't be the first one you've chosen or the second, but it can be any other, right? And this goes all the way down, and you have to think a little bit to figure out where it stops. But where it stops is m minus n plus 1, right? If you think about, for example, small values of n, this will be clear. So if m, for example, e.g., if n equals 2, let's say n equals 3, right? What you get is m minus 1, m minus 2, and m minus 2 in this case is m minus n plus 1. Okay. So this is kind of the right place for it to stop. And that is, if we look back at the previous slide, that is what Pmn is. So Pmn is m factorial over m minus n factorial, which is this expression. Okay, and I should, just to make sure we explain the reasons, so here what I use is the product rule. Because choosing a permutation is the same as choosing the first element and choosing the second element and the third element and the fourth and so on. Whenever there's an and involved, it's usually the product rule. Are there any questions about this? So let's do an example to kind of solidify how you use this idea. So suppose that in whatever place you're in, whatever province or state or whatever country, the license plates always have 3 different letters followed by 3 different digits. How many license plates are possible? So how many ways can we pick 3 different letters? Well, the number of ways to pick 3 different letters is going to be, and these letters come in order, right? So on the license plate. So, you can do it directly by just saying 26 times 25 times 24, but also you should recognize that this is the same as P26(3). Okay, so by the proposition from the previous slide, the number of ways to pick 3 different letters in order is P26(3), because that's the number of permutations of length 3 of a set of size 26. Okay, and then you have to pick 3 numbers, and those numbers, I didn't put any restrictions, so they can be anything between 0 and 9. So there's 10 choices for the first one, once you've chosen the first one, there's 9 and then 8. Okay, and you should recognize then, so that this is P10.3. So by the way, if you just write the answer P26.3 times P10.3, this is perfectly acceptable. So just so you know, you don't have to write out all these products or something. Ooh, right. That's a good question. It didn't say distinct here, did it? Right, so let's then say, yeah. The thing is, I figured these, I came up with these things in advance, and then I read them very quickly when trying to go through this. But that's a very good point in the chat. I didn't say that the digits have to be distinct. So for the digits, actually, they could all be the same. It doesn't matter. So that's just a string of length 3. So that should have been 10 to the 3. Thank you for that. Please do point out when I make mistakes here, because it will happen. Right, so just to clarify, the last 3 characters of the license plate, they have to be digits, but there was no restriction that they have to be distinct. So it's just any string of length 3 from an alphabet of size 10, so you have 10 to the 3. So yeah, just to clarify, so on any assignment, you don't have to compute numbers. If you just wrote P26.3, 10 to the 3, that would be perfectly acceptable. The quizzes are going to be a little bit different because I want them to be marked by Brightspace automatically. So for the quizzes, you do have to compute numbers. So you may want to use calculators for that, or a calculator, or use your browser or whatever. Is that clear? Okay. Thank you for pointing out the mistake. Okay. Oh yeah, so this is what I mentioned before. It's fine to just leave things in the notation we've defined in the course. So P27.7 to the 72, that would be a perfectly fine answer. And that also applies to tests. Okay. Yeah, so that's it goes both ways in terms of this. So like if you did compute 10 to the 3 and write 1000, that's fine. If you write 10 to the 3, that's fine, as long as it computes to the correct number. Okay, and I would say don't put it in a complicated format so that it computes to the right number, but it's hard to tell. But basically, any kind of reasonable version of the answer would be fine. So if you wrote P26.3 times 1000, that's fine, for example. So now that was permutations. Oh, I should say, yeah, Brightspace. So I'm going to try to make this clear on every quiz. When you do it on Brightspace, just write a raw number, right? Just compute the actual number. Yeah, Brightspace isn't necessarily that bright. But on CrowdMark, all your things will just be written. Either you'll type them or you'll handwrite them, so that's fine. But Brightspace is a bit different. It'll have to be a raw number. Okay. So let's now talk about a very related topic, which is the idea of combinations. So we did permutations, now we're doing combination. So let's say that X is a set of size n, and take K between 0 and n. So we define n choose K, which is written this way. So with parentheses, so you write parentheses and you write n on the top and you write K on the bottom. So it's not a fraction. So please don't put any horizontal line between them because it'll just be confusing. But the notation is you just write n on top of K with parentheses. So we let this denote the number of subsets of X of size exactly K. Okay, and the way that this is pronounced, so when you see this notation, this is pronounced n choose K. Now, this is kind of the preferred notation for this concept. Unfortunately, if you, for example, writing in Brightspace, Brightspace is okay, but for example, writing, if you're just writing text, you can't make this, right? You can't write letters on top of letters, in just simple text. So unfortunately, this notation doesn't, we need a kind of alternative notation. So sometimes we write this as CNK, which is similar to the PNK notation. So if I write CNK, or if I write this n choose k, this notation, they mean the same thing. It just happens to be that sometimes I can't write them. I can't write it this way. I have to write it that way. Okay, is that clear? Does everyone know what I mean by things like subsets and stuff like that? Oh, yes, so this is what I just explained. So it's pronounced n choose k, and you can write it either way. But usually the preferred way to write it is this notation here with n on top of k. So how big is n choose k, or what is n choose k equal to? Or let's just think of let's just list them out, right? So what are the subsets of 1, 2, 3, 4 of size 2? Does anyone have? So what's an example of a subset of size 2? Yeah, these are all good examples, right? So 1, 2. I'll go through them this way. So 1, 2, 1, 3, 1, 4. So just all the ways of choosing two elements. Yeah, 1, 1 doesn't technically work. So that's the difference. That's actually an important difference, because a thing to note or think about that I'm not talking about strings here, right? Because if it was a string, you can have repeated elements. But a subset is just, you just choose elements of the set, and you're only allowed to choose them once. So this is actually a good example coming from the chat. So for example, so 1, 1 would not count. So it's not a subset. Well, it is a subset. Well, it's a subset that has size 2. So if you write a set in set notation, if you have repeated elements, this is just equal to the set, which just contains 1. So this has size 1. Okay. So how many subsets are there? So there's 6. So therefore, well, I'll write it like this. So I'll write 4 choose 2 is equal to 6. Is this clear? Obviously, we want a better way of counting or computing 4 choose or n choose k, which doesn't involve listing all the subsets, because that could get a little bit, that could take us a long time. So we want to have a formula for n choose k. Okay, so I claim that, so this is what I'm going to prove, that n choose k is equal to pnk divided by k factorial. But remember, we know what pnk is, right? So I'll just say that this is the same as, because we can substitute in for p and k, this is equal to n factorial over n minus k factorial, k factorial. So this is, I claim that this is a formula for n choose k. So the number of subsets of a set of size n which have size k. Any questions? So I'm gonna now give a short proof of this. So remember what p and k counts. It counts permutations of length k using elements of a set of size n. Right, so this counts permutations of 1, 2, up to n of length k, which is, remember what a permutation is, that's just a string where all the letters are different. So it counts the number of ways to list out numbers from 1 up to n so that you never repeat a letter or a number. Okay, so imagine I have a subset of size k. How many ways can I turn this into a permutation? Meaning, suppose I take the numbers 2 and 4, which is a subset of 1, 2, 3, 4. How many ways can I make a permutation of 2 and 4 of length k? Or sorry, of length 2. Actually, maybe for this, I should say here, if I take a subset of length k, I'm trying to count the number of ways it can be turned into a permutation of length k. That's important. So if I took, suppose I take a set of size 3. How many ways can I write those elements, those 3 elements, as a permutation of length 3? Does anyone have a guess, an answer? Or if I take a thing of size, so 6 is right. And 6 comes from 3 factorial, right? Because, there's 3 choices for the first, 2 choices for the second, 1 choice for the third. So it can be done in k factorial ways. Okay, Or you could think of this as it can be done in, so k factorial is the same as p kk, right? It's the number of permutations of a set of size k which have length k. So therefore, basically I have a kind of correspondence. I have, if I take a subset, I can turn it into k factorial different permutations. If I have a permutation, I can turn it into a subset by just forgetting the order. So this actually proves that, well, p n k is equal to k factorial times n choose k. Because, yeah, basically choosing a subset and then arranging those subsets, or that subset in one of the different k factorial ways, is the same thing as choosing a permutation of length k, right? And the number of ways to choose a subset and then arrange it is on the right side. It's first you choose the subset, then you arrange it. Basically, this is the product rule here going on. And that's the same thing as just choosing a permutation. Okay, this is a little bit confusing. You don't necessarily have to remember the proofs of these things, but understanding the kind of idea is, well, yeah, I would even say that understanding the reason why this is true is better than understanding the formula, but yeah, if you understand the formula, that helps as well. But are there any questions about anything here? Okay, so now let's, so I have another proposition, so which says that for k between 0 and n, I want to prove that n choose k is the same as n choose n minus k. So this is just a nice fact, which is sometimes very useful. Does anyone have a reason why this would be true? Can anyone tell why? So remember, n choose k counts subsets of size k from a set of size n. N choose n minus k counts sets of size n minus k. So why would these things count the same? Why would they be the same value? Okay. Anyway, so the reason is because of the formula. That's one reason. I mean, yeah, that's one way to do it. Count ways to exclude things. Count. Yeah. Yep. So these are all valid proofs. Yeah. So one nice observation is, yeah, as we have just proved, this is n factorial over k factorial, n minus k factorial. It doesn't, okay, I wrote these in a different order, it doesn't matter. N minus k, you know, it's the same. By the formula, that's one proof. Another proof, which is kind of nice because it's intuitive, is that, yeah, counting ways of keeping k items is the same as counting the number of ways to throw away n minus k items. So in other words, yeah, if I take, you know, well, maybe I'll just kind of write that. So, well, counting subsets of size k is the same as counting ways to, say, keep k elements of 1 up to n. But of course, if you keep exactly k elements, it's the same as throwing away n minus k elements, which is the same as counting subsets of size n minus k. Sorry, this got a bit squished at the bottom, but yeah. So thank you for those answers. That's exactly what I was going for. Okay, so this is just a nice kind of combinatorial identity. Okay, just an example. So how many subsets have size 3? Subsets of 1 up to 7. And like I said, in an assignment or in a test, you can just write 7 choose 3. If we wanted to make this more precise, well, what do we have? So 7 factorial over 4 factorial, 3 factorial. 7 times 6, 5. I could go times 4 times 3 times 2 times 1, but actually I don't need to because you have some cancellation here. So this 4, that has 4, 3, 2, 1, so that cancels with the 4, 3, 2, 1 up above over 3 factorial, which is 7 times 5, which is 30. Just going through an example of how to actually compute these things. And then 7 choose 4. Well, once we know 7 choose 3, we don't really have to think. because it's 35, because 7 choose 4 is the same as 7 choose 7 minus 4, which is 7 choose 3. So this is by the previous slide. This. Yeah, maybe let's, okay, we can do this. So in the lottery in British Columbia, the BC 49 lottery, you pick 6 numbers between 1 and 49. You win if all of your numbers match the ones that are drawn, okay? But they don't have to be in order. So how many different ways can different ways can you choose the numbers? And remember, the order of the numbers doesn't matter. So any thoughts about that? How many sets of, and the numbers have to be different. You can't just, it'd be great if you could pick the same number every time, right? Because I could pick 5, 5, 5, 5, 6 times, and then if a 5 comes up, I win, but you have to pick different numbers. Yeah, so that looks correct. So the answer is C, 49, 6, or in other words, 49 choose 6. But you can see that now if you try to write it in the chat, you have to write it with this C notation, unfortunately. What's the probability of winning? Well, does anyone know? I mean, in terms of what would it be? How would you compute that probability? Yeah, so you would take 1 over the number. So what is that? So the actual number, this, yeah, approximately 0. Yeah, so we're looking at, so in the chat, we're looking at 7.15 to the, times 10 to the minus 8. A rather small chance. Okay. This is a kind of a nice way to think of things, is in terms of putting balls into bins. So suppose that you have n bins. So for the lottery, so that, yeah, that's the thing is, so there is a kind of a natural question here. Is the lottery, should you be thinking about permutations or should you be thinking about combinations? It should be combinations, because if I choose the numbers, so the way that you win the lottery is that you have to get the right numbers, but they don't have to be in the right order, right? So if they announce the lottery numbers, you have to match all the numbers, but you don't have to match the order. So if you had to match the order, it'd be a permutation. Since only the set of numbers is all that matters, it's a combination. It's just a, 49 choose 6. But that's a very good question. Okay, so a lot of these questions can be thought of in terms of balls and bins. So imagine you have n bins and you have m balls, where to clarify, so m here is at most n. So n, they might be equal, or n might be bigger than m. So you have more balls than bins, or at least as many balls as bins. Each bin can only fit 1 ball. So how many ways can I put the balls into the bins? We're going to kind of think of this in 2 different ways. So first, suppose that all the balls are identical. So you can't tell the difference if you switch, 1 ball for another. So how many ways can I put the balls into the bins if all of them are identical? Sorry, the bins are all different. I should make that clear. The bins are labeled 1 up to n. All the balls are the same. And every bin can fit only 1 ball. Right, so yes, we've got an answer coming in, and that looks correct to me. Let's think about it. So if all the balls are identical, then really all you're doing is choosing m bins. Because if you choose m bins, you just put 1 ball in each, and you can't tell the difference, so it doesn't really, it doesn't matter which ball you put in them. And conversely, if I put balls into bins, that's the same as choosing those bins. So yes, so the first answer is n choose m. Now if all the balls have different colors, that becomes different, right? Because if I put the red ball in the first bin, the blue ball in the second bin, that's different than putting the blue one in the first one and the red one in the second, right? So here's a way to think of it. Think of the balls, instead of having different, well, you can think of it in lots of different ways, but one way you can think of it is think about the balls being numbered 1 up to m instead of colors, right? And then you could look at where you put ball 1, and that's in one of the bins, 1 up to n, and you can think of that as being the first. Okay. You can think of the place you put ball 1 as being the first element of a permutation. And then you can think of where you put ball 2 as being the second element of a permutation, where the alpha bit is 1 up to n. And where you put ball 3 is the third element, and so on, right? So this is indeed equal to the number of permutations of numbers 1 up to n, where the length of the permutation is m. So a way to do this is think of the balls as numbered. Okay. Any questions about this? Yeah, okay. So does anyone know the answer to this? How many, so do we remember what a binary string is? So binary string is a string where all of the entries are 0 or 1. So it's a string with alphabet 0, 1. Yeah, so this is, the purpose of this question is kind of making you think about one of these concepts we've been looking at in a sort of different way, but it turns out to be equivalent. So yeah, so the answer in the chat is correct. So the number of binary strings of length n with exactly k ones, the answer is n choose k. Why? Well, the reason is, so if you think of a binary string, let's say 0, 1, 1, 0, 1, of length 1, 2, 3, 4, 5, let's say, you can think of this as, so you can think of it as you have your numbers 1 up to 5, and you can think of the ith digit of the, you can think of the binary string as corresponding to a subset of size 3, in the sense that the first digit tells you if 1 is in the set or not. So if it's a 0, you put 1 in the set. If it's a 1, or sorry, if it's a 0, you don't put 1 in the set, and if it's a 1, you do. Right? So in this sense, this binary string corresponds to the set 2, 3, 5. So just to make it clear, I'm thinking of the first digit corresponding to 1, 2, 3, 4, 5. So the fact that the second digit is a 1 says 2 is in the set. 3, the third digit being 1 means 3 is in the set, and the fifth digit means, or the fifth whatever letter means that 5 is in the set. Right? So in this way, you can think of it, yeah, if you think about it, these binary strings with k1s correspond exactly to subsets of size k. And remember, in the very beginning, we defined n choose k to be the number of subsets of size k from a set of size n. So indeed, it's n choose k. How many ways can we choose a committee of 4 people from a committee of 20 people? Okay, these are getting maybe a little bit redundant at this point. I'll just write 20 choose 4. You've got 4 people, or sorry, 20 people. You need to pick 4 of them for the committee. It's 20 choose 4. So it's a subset of size 4. Now here it becomes a little bit different. So what if we want to pick a committee, but actually this committee, the members are not all equal? So you have a committee where there's 4 different positions. You have president, vice president, treasurer, secretary, for example. So there's a question in the chat that about permutations and combinations not allowing repeats, and that's correct. So so that kind of goes back to the thing we had before, that you know, if I take the set containing 1 and 1, that's not a set of size. That's not a subset of size 2 of 1 up to n. So yeah, both of these things, neither of these things have repeats, and it makes sense, because if I'm for these problems, because if I'm choosing a committee of 4 people, I wouldn't put myself in that committee 4 times. So these things all kind of match. Yeah. So the order matters here, right? So for this question, so committee has 4 different positions. So what would be the answer then? Yeah, so it's a permutation, exactly. So we've got P 24, which you could, if you just think of the rule of product, you could just deduce this, right? It's 20 choices for the president, and so on and so forth. But really, you should get good at kind of memorizing what types of questions correspond to permutations and what types of questions correspond to combinations. So this is 22, or sorry, P24. Okay, trickier one. 7 friends go to a movie. One of them, who's named Jaehoon, is mad at Lena, another one of them, and he refuses to sit next to her. How many ways can you arrange these friends assuming that they all sit in the same row. So they all sit in 7 consecutive seats. How many ways can you arrange them so that everybody's happy? So Jaehoon doesn't have to sit beside Lena. Okay, well, I've got a hint here which says complement, and that's what I'd like to use. So, right, so if I was just organizing them, if I was just organizing them in any way, I would have 7 factorial ways of doing that. Or in other words, P77, right? Because I'm taking 7 objects and permuting 7 of them. Okay. And now I want to subtract the bad ones. So I think this is the right idea in the chat, but maybe the wrong numbers. But yeah, the number of ways to just permute them if I don't care about if everyone's happy is just 7 factorial, which is P77. Now if I care about, if I'm subtracting the ones where they sit together, how many of those permutations are there? Well, if you think about it, yes. So there's something in the chat saying 2 times 6 factorial, which is correct. Now how to think about that is basically imagine you glue these 2 people together, right? And there's 2 different ways to, and then you permute everybody else, right? So a permutation where they sit together is the same as kind of putting them together and then permuting everybody, treating those 2 people as one person. And there's 2 ways to glue them together. You can put Jaehoon on the left and Lena on the right, or Jaehoon on the right and Lena on the left. So there's 2 ways of gluing them together. So there's 2 ways, or in other words, actually, really, it's the 2 comes from 2 factorial. So 2 factorial ways to arrange. I'll just put J and L. Okay, and if I say that they have to be put beside each other, then I'm treating them as a single object, right? Basically, well, so this is the final answer. I'm sure you guys can hear my dogs going completely crazy downstairs. Sorry about that. But yeah, so how is it 6 factorial? So the way to think of this is how do we count permutations where they sit beside each other? You kind of put them together, right? J, L, and I don't know who the other people are called. Let's call them X, Y, and Z, and W. And you think about, so putting those 2 people together is the same as putting them in a kind of blob, and then permuting. Let's say I put all of these ones go into separate blobs. Wait, 1, 2, 3, 4, 5, 6 people. I need another person. Yeah, A. Right, and now it becomes 6 objects which we permute. Okay, but also you have to think about the fact that they can be permuted within themselves. So it could go J on the left, L on the right, or L and then J. So that's where you get the 2 from. Okay, so yeah, so here we're using a few different concepts together. Any questions about that? So often in these questions, in the assignments and stuff, you may have to use more than one different concept altogether. Okay, so at the SPCA, there's N dogs and M cats. How many ways are there to choose 6 animals? Well, it's just this, we're just looking at subsets of size 6 from a set of size n plus m, right? So here we didn't care whether they're cats or dogs. We just pick 6 of them. So we have a kind of pool of n plus m animals, and we pick 6. So it's n plus m choose 6. And we didn't care about the order we choose the animals. We just want to choose 6 of them. 3 dogs and 3 cats is going to be then. So there's an answer in the chat which is close, but remember the importance of this word, and. Okay, so when you do things like this, you choose the first thing and then you choose the second thing. It's usually going to be multiplication, right? So n choose 3, m choose 3, because there's n choose 3 ways to pick 3 dogs, m choose 3 ways to pick 3 cats, and it's the rule of product. No. So this is the last example we'll go through. Yeah, so basically, I mean, this lecture has been mostly examples, but that's really what that's really the key to this course, is knowing how to recognize what rules are being applied in what examples. So, if you are having a difficult time with this to figure out which things to apply at what time, I really do recommend trying some of the practice problems because, you know, because they also have hints and solutions. So that should help you to kind of get experience recognizing these things. Okay, how many permutations of 1 up to n are there such that all of the odd numbers come before all of the even numbers? Yeah, maybe I'm actually going to change this because this is annoying. Sorry, because the thing is, yeah, I don't want to deal with odd, you know, the fact that n could be odd or even. Let's say instead of 1 up to n, we have 1 up to 2n. So there's a question in the chat whether 2 undergrads put together the solution manuals for the practice problems. The answer to that is yes, but that was done under the supervision of a faculty member, of a professor. So they worked over the summer, like they were paid by the department, I guess, or by some kind of funding, and their goal was to put together these this comprehensive list of problems and solutions. So yes, but it wasn't just undergrads kind of going off on their own. It was supervised. Okay, so I've kind of changed this a bit. So how many ways can we permute the numbers from 1 up to 2n so we write all of those numbers down so that all the odd numbers come before all of the even numbers. So if you think about this, what you could think of is, so there's n odd numbers and there's n even numbers between 1 and 2n. You could think of just taking out the odd numbers, you know, shuffling them around, permuting them, and then writing them down. Taking out all the even numbers, shuffling them, permuting them, and writing them down. Right? That's the same thing as this kind of permutation. Yeah, so indeed the answer is going to be n factorial times n factorial, because, and the way you get this is that, you know, there's n factorial ways, you know, to permute the odds, and there's n factorial ways to permute the evens, and we have to permute the odds and then permute the evens. So since we're, you know, doing this and that, it's again the rule of product, so it's n factorial times n factorial. And if you didn't think of it this way and you didn't use the rule of product and you just kind of started thinking of it like there's n choices for the first one, n minus 1 for the second, until you run out of odd numbers, and then you have n choices when you get to the first even number, and so on and so forth. Okay, so this is all I wanted to really do in this lecture. Are there any questions? Okay, if not, oh yeah, so maybe I should emphasize this. So I sort of mentioned this in the introduction last time, but it's maybe it slipped by a few people. So there's this schedule for the whole course. So I'll put I can go back to the cats and dogs slide, yeah. But let me, okay. So I put a link in the chat. This schedule should really be something that you go to, you know, if you want to look for anything, this is the best place to find it, pretty much, except for quizzes. So the lecture slides are already on this schedule. So if you look at lecture 2, and even the next lecture ones are there too, and if you click slides, lecture slides for lecture 2, it should come up in your browser. And if you take a look now, you'll see that even the stuff I've written, you know, a minute ago.
I think we can see what you're doing right now.
Oh, yeah, no, I put it into the chat. Okay, I can. Okay. Yeah, I just wanted to leave the slide up there because someone was looking at the dog and cat slide. Yeah. Well, yeah. Basically, if you, but yeah. So in the chat, there's this link to the schedule. If you go to the schedule, you can see the lecture slides. And those will, for every lecture, I'll put them there. So that should, you should be able to find them there. And as I write on them, the writing should appear on those on the online version. Okay, so let's end there because it's basically 12:50. So yes, practice problems. So in the course outline, all of this information is there. So just, you know, but this is the course webpage I put in the chat. So that's where the practice problems can be found. But yeah, please, you know, do take a look at the course outline, read it carefully, everything that I'm explaining is in there in terms of where to find things. Okay, thanks.